We're going to start day 3. We have our speaker here, Dr. Krzysztof Geras from NYU. He's here going to give 2 lectures in NGSchool, but today it's about model explainability. So yeah, I hope you guys will be excited to listen to this talk, and feel free to ask some questions. I'll give the floor to you.
Thank you. Okay. Okay. I mean, if you're ready, I think maybe we should begin. Because you're already a little bit after when we're supposed to start. Okay. So I think maybe let me start with saying that really the only purpose of this talk is that you learn stuff. I don't earn any points by doing this, really. And I'm not even a computational biologist, so I'm not going to judge you, right? I hope that. So you can ask, whatever. So really, you can ask questions whenever you want. It is just a lot more interesting, when people ask questions, then I just keep talking for an hour and a half. And I think it's also more interesting for you. I think during the pandemic, everybody had an experience of looking at a Zoom where everybody has, screen off, their camera off and their microphone off, and it's like talking to your own hand. And I think it is, I think since we are here, I think it's a great opportunity to, to not do that. So really just, I think if you have a question, then possibly a lot of you have similar questions, and I imagine that also you are not, I think your main thing is computational biology, not machine learning. So, so just really just don't hesitate. And I have some slides, of course, but in reality we don't really have to go through them. It's really, so we can go through my slides, or we can just stop at some, or we can just stop in the middle and just not go through all my slides. I honestly, I think as long as a lot of you increase their knowledge by the end of this lecture, I'm happy. I don't come here with a purpose of showing everybody what the slides I created. And I think especially coming to a summer school like this, I think it's a better approach to this. I think there are kind of 2 goals of what's happening here. I think one goal is that you should, yes, sure, you should get some kind of a broad idea of different things, but but I think in general in science, I think it's more important that you understand like a smaller set of things very deeply than about existence of things, right? So like a journalist can know about a lot of like 20 different things, and they can have a broad idea, but I think you should. But I think for you, I think you should really just try to understand maybe some things very, very well, and then maybe I only know about the existence of some things, some other things, but there has to be something that you are really expert in. And and of course I'll give you some pointers, and I want to show you different elements of machine learning and enable you to self-study effectively, because of course I cannot teach you everything in an hour and a half. So I think so maybe a few years ago I was invited to a conference on medical imaging, and I was asked, how to learn machine learning, and I said, look, people, just machine learning is not a Python package. It's like science. You have to actually learn some math, right? And that was that's kind of limited their enthusiasm. But really, okay, so machine learning is a bit of a constantly evolving science. It's not very consistent. It's a very young science. just like maybe physics used to be around the time of Isaac Newton. We are only discovering some principles, and but nevertheless, it's a science, right? So you cannot expect to learn everything in an hour and a half. I think you should just like understand the broad spectrum, maybe understand some things very well, understand the existence of some broad spectrum of methods, and then go home and watch like 10 times more lectures. Actually, maybe even read a book, read some papers, and actually study yourself. And as you might have heard earlier, right, there exists a difference. Let's say there exist multiple machine learning tasks, such as regression. Maybe I guess you probably already have heard of regression. I've seen some regression equations here. There's also classification, which you probably have also heard, but there's a wide variety of machine learning tasks, right? So it's like image generation, for example, which cannot really be, which is not neither directly regression or classification, but a lot of tasks in machine learning, in fact, are some combination of regression and classification, right? So if you think about, for example, if you think about segmentation is in fact pixel-wise classification, right? And you can make these kind of reductions for a lot of tasks in machine learning. But so if you just understand classification, so if you understand regression classification, then you actually understand quite a lot of machine learning already. So here, for the purposes of this talking about explanations, I think we'll focus on classification. Okay, so maybe this is a bit of a philosophical question, because what is model explainability? Because nobody really knows. It's because it's such a broad term. So what I am going to, the way I guess my private definition is that we think about explainability is we're going to think about whether we can explain certain model decision process in terms that are understandable to us. Let's say human experts, right? Because we are all experts, obviously. But there's no really. Let's say this is a definition I came up with myself last night when I was actually thinking about this slide. But if you ask probably 10 different people, they're going to tell you something different. And that's and actually I even once like was writing a paper with my students, and they actually in the middle of writing it was a paper about explainable models. We were thinking, what's actually explanation? Okay, and also explainability is often interchangeable interpretability and also intelligibility to an extent. So you can come up with these two terms. I think the differences are between these terms are kind of subtle enough that between explainability and interpretability, maybe there's not worth pondering this too much. Intelligibility is related to explainability and interpretability, but typically the way when people talk about intelligible models, they don't talk about explaining an existing model, but actually like building a model which is easy to understand from the outset. Okay, and this is really a set of model-dependent techniques rather than a consistent science. So there's no so just like there's maybe if you think about there's regression, machine learning. So I guess machine learning is such a science. There's regression, classification, other things, different methods. This model explainability really applies to different bits of machine learning. So it's but I will show you what it means. And and there's also when you talk about explanations, you can think of model level explanation and example level explanation. And what I mean by that is we can look at an entire model, whatever it is, and we can somehow try to interpret what it is learning, or we can look at a specific example and we can try to see what this model did to arrive at the specific conclusion for this particular case. And these are often not the same thing. Okay, and then there's also types of methods where you actually train a model, and then you try to somehow understand what it has learned, again on either model level or example level. And there are also methods where you try to embed explainability in the process of the training of the model, so that sort of you don't have to do this extra effort post hoc. Okay. All right. Okay. So here. Okay. Maybe let's pause here for maybe 30 seconds, and you tell me whether like what like whether what if you have any questions about what I've said so far, or you have maybe I don't know some kind of conclusion that you want to share with everybody. Okay. Yeah. Sure.
I have a question about explainability on this episode. The way we usually use you want to get causality, you want to know what causes the outcomes of the model.
Oh.
The explanations that you usually create seems like they may be statistical.
Mm-hmm.
What do you call the link between causality and explainability?
So I think ideally we would like to have some kind of causal explanations, but I don't think you can. But I think these methods that we currently have, I don't think you can necessarily interpret them this way. So I think there's I think this is okay. So this kind of causal explanations is something that I have seen people targeting maybe in the last year or two, but I don't think that these kind of methods have really yet made it to the mainstream. But you're right that ideally you would like to have some kind of, let's say you would like this interpretative method or explainability method to somehow extract some kind of a causal model of what's happening in this model. But unfortunately, that's not really like we haven't yet reached this kind of level of sophistication of these methods. Okay, so let me first begin by this very simple example of of what explainability means in decision trees. So this is so these are the different irises. Well, these are flowers, right? And this is okay. There's a very famous data set called iris data set. If you ever have done any exercise in machine learning, you will encounter this data set. It's in this ancient library of data sets called UCI. I think it's called UCI machine learning data set repository or something like this. And the task for which this dataset was designed was to distinguish which of these three types of flowers it is based on petal width and petal length, right? Just these two features. So let's say translating this to very simple machine learning terms. You have, let's say, x1 is petal width, x2 is petal length, and then let's say y is the specific species of the iris. And probably the most commonly applied model to this data set is decision trees. Have you heard of decision trees? I mean, okay, so maybe, you know what? Maybe close your eyes and raise your hand. No, close your eyes so that people don't judge you. I know, I'm serious. Seriously, close your eyes so that everybody can see, and then raise your hand if you have heard of decision trees. Okay. Thank you. Okay, so not everybody. Okay, all right. Okay, that's fine. Okay, so basically, decision trees is this very simple model where you basically are initially trying to build a decision tree, right? So what it means is that, so let's say forget about the training and how to create this tree, but if you are given this tree, what you're supposed to do is you're supposed to go to the top, right? Like go to the top, like let's say start here, and then look at the feature petal width, and then if it's smaller than 0.6, then you say this is this particular species, Iris setosa, with very high probability. Right? Or if you go to the right, if it's greater than 0.6, then you look at the feature petal width again, and then here, again, if it's greater than 1.7, then this is Iris virginica, and if it's smaller than 1.7, you look at petal length, right? And you basically you try to reach the leaf of the tree. And so this is a very simple model, but it works very well for data like this. And you can also obviously so we know there is So this used to be like a hot thing in the 90s and 80s. And and there were like entire conferences of people who were studying methods for training these models. And this is still a very strong model for example, it's still a very strong model for tabular data. And in fact, if you ever look at Kaggle, people think, people these days, people think that, that like deep learning is is the best kind of thing. But if you look at Kaggle, then probably still, still probably like a lot of competitions are won by some very exotic decision trees. Because there's, this is basically, this is like decision tree 101, but there's like, but there are some really complex decision trees. Right, so there's decision. So there are, you can form forests with trees. If you have very many trees, you can create ensembles of forests, etc., etc. But in this very simple, but a great advantage of this decision tree model is that it's incredibly simple. So you can have both a model level explanation, because you understand exactly what's happening here, right? Because this is small enough, right? But also, if you look at a specific example, then we can follow this path, right? And you can say, okay, this particular iris is whatever type of iris, because it has petal length in a certain range, right? So a petal width within a certain range. So it's you see, so basically in this kind of simple models like decision trees, you really get explainability sort of for free, right? Because it's just simple enough that, well, it's just there, right? You don't need any kind of extra. You don't need anything extra to extract explainability from this. Okay, does this all make sense? Okay, cool. Okay, now this is a very interesting model. I don't know if you have heard. Have you heard of k-nearest neighbors? Have people told you about it? So it's also a very simple machine learning model where so if you want to classify a certain point, you just look at its neighbors. And let's say this is the training data, right? But let's say that I have a test data here, right? So all that I will do is just maybe look at my nearest neighbor, right? So it's a red point, so that's why all this area is red, because the red point is the closest point, right? And here, again, explainability is, there's a very natural form of explainability in this kind of model. Well, it's similarity-based explainability, right? So basically, you would say, let's say, if these were, so you can imagine that. So we can imagine that this is this iris data set as well, because it has 2 dimensions and I think 3 classes. But you can build such, such explanations in a much more complex ways, right? So, for example, you could maybe have some kind of, perhaps have some kind of complex data embedded into 2 dimensions, and then compute these kind of, these neighborhood maps in these 2 dimensions, and then you can also explain what's going on with, just by looking at the neighbor. Yeah. So but again here you you get the explainability just by for free. Okay. Now this is have you heard of the district regression? I assume you probably have. Okay, so we are here I need you to focus a little bit more. Because this is not a very complex equation, but I think this is actually probably the most important equation. Now you would be surprised at how much people do with this equation and similar ones. There's actually, there are people who have spent their entire career studying this. Because so here what we have is, again, so the x is some set of features, and beta are the parameters, which are learnable. So this is a vector of learnable. So both x, so both x is a vector, and beta is also a vector. And and p hat is a prediction of the probability that x belongs to a positive class. Right. So we are assuming here that we are assuming here just for to make it easy that there's only positive and negative class, and we want to predict which one x is. Okay, and here, okay, so you can actually, okay, so there are some very good reasons why this equation looks like this. If you think about it, okay, so if you think about this, it's actually, it's a little bit unexpected, right? It's a little bit like, this is kind of a strange form of an equation, but it really works. And there's a justification for this functional form of why this looks like that. So you just maybe, I can explain this to you, but maybe you can also look it up in Wikipedia or something. But here, this model is a parametric model. So there are certain parameters here, and beta, and so there's the beta 0 with the entire vector beta that governs the prediction of this model. So in comparison to something like K and N, it becomes a little bit more complicated. Because we have to, we have to learn these parameters, which actually isn't easy. If we have, it is trivial in case of something like this iris data set, but people train these kind of models on, like sometimes millions and millions of data points, and then optimization, even though this is, complex optimization problem, it becomes very difficult to actually optimize this very quickly. So like a lot of, actually I would say, so a lot of people spend their entire career trying to optimize this quickly. To learn this quickly. Learning is a different story here, but anyway, but here in these kind of models, you can interpret this model by looking at these parameters. Let's say, so if they are positive, so if this parameter is positive, then you can say, oh, okay, okay, maybe let's say, okay, so let's just say that like this parameter, let's say this x is always positive to make it easy, and then this beta, and then you look at the beta, and you look at the, and you say, oh, like if you train it, and then you can say something like, oh, like if beta is positive, then it means that it is supporting that it's important for this I parameter for a certain class. This I parameter is important for a certain class. You can make these kind of inferences. You can imagine, right? Of course, that's okay. That's a very weak form of explanation. But this is what you can do in these kind of models. Okay, now you might have heard of this explainability, expressivity, or explainability accuracy trade-off. This is kind of something that if you listen to 10 lectures on explainability, like this is going to come up like 9 times out of 10. But you should be a little bit okay. So it is true to a certain degree. So it is true that typically the simpler models, which are easier to explain, such as decision trees, are not very expressive. In the sense that if you have just if you have like a simple decision tree and you limit its depth, you cannot express very many functions this way. And also, the logistic regression is also not very expressive in the sense that all you can do is to draw a linear decision boundary between points of the two classes. So that's okay. So that's true for some models. So it's very easy to understand what decision tree encodes, but it's hard to understand what a deep neural network does, what knowledge it encodes. Okay, however, you should interpret this carefully. Well, because, for example, a k-nearest neighbor can actually represent any classification surface. Right? So, in fact, it is the most expressive model, but it is very explainable, right? So, it is. So there are some. Okay. So this is a. So there are some kind of exceptions to this kind of alleged trade-off. So I guess I'm kind of repeating this because you will hear that. So I would like you to know that this kind of, let's say, this exists as a topic, but I would, at the same time, I would like you to not be a little bit skeptical about this when people say this, because it doesn't necessarily mean it's not 100% correct. And also, very often, embedding explainability to the models actually improves generalization. So, so what I mean by generalization is, let's say, classification, like the quality of predictions. Because if you embed, so in a very abstract way, you can think of embedding explainability as a form of regularization. So maybe in linear regression, like L1, like have you heard of L1 regularization in linear regression? I guess you must have.
Yes.
Yesterday. Okay, so so let's say L1 is a very simple form of regularization of a linear regression, and you can think of essentially you can think of as regularization being any form of constraint for the model. And explainability is one form of it. It's a very weird form of a constraint, and it's often maybe not necessarily easy to express mathematically, but it is nevertheless a form of you can think about it as a form of a regularization for the model if you embed it into the model. So if it's a good regularization, you can actually improve the accuracy rather than lose accuracy. So that's why this kind of, let's say, this explainability, expressivity, or explainability accuracy trade-off, I think it's something that you should be cautious about this. Okay, so I think I've talked about enough about those very simple models, and I'm going to now. Okay, and I'm going to focus now more on deep learning, because I like deep learning and it's amazing. Okay, so I guess you must have heard of deep learning, right? Okay, let's keep closing eyes. Who has ever trained a neural network? Could you raise your hands? Oh wow! Okay, this is amazing. So now everybody trains neural networks. Okay, cool. Okay, great. So so for those that don't know what a neural network is, it's you can think about a neural network as if it was something very similar to somehow something similar to logistic regression, but having some kind of hidden layers, right? So it's in a very crude way. It's just like, so when you have logistic regression, you try to learn, try to learn from X, and you try to predict Y, right? That's kind of. So X is the features, and Y is some kind of a prediction, right? So let's say in the classification or regression, and and for deep learning, there's deep learning is a very broad. There's a very broad family of methods, but to put it very simply, you basically instead of going just from X to Y hat, you have some kind of intermediate versions of this data, right? So you actually, so you don't, so you know, if you define these intermediate versions of the data in somehow a convenient way, they're going to make it easier for you to classify X into Y hat, right? So you know, so for example, if you know, like, well, this could be really anything, just any, you know, like really any function in the most standard, you know, in the most standard, like in the most classic machine learning, you know, like let's say deep learning or like neural networks from the 80s or the 90s. To create this hidden layer, you would just typically do a matrix multiplication and a nonlinear function. You know, of course, it's some things have changed since then. So now these, you know, this matrix multiplication has some kind of a special structure. These, you know, linear functions, you know, have become different, have become complicated, etc., etc. But you know, but the essence of deep learning is just the idea that learning not just the final predictor, but some kind of intermediate representations for the data is, you know, is a kind of a good prior for thinking about how learning should work. And you know, and I'm sure you have heard that. I'm sure you have heard of, you know, like deep learning in many different contexts. But so actually, if there's time, I'm going to show you an example of a deep learning project that I work on my own. That, you know, and kind of how these ideas of explainability fit into that. We'll see if we'll get there. Okay, so by the way, is there, okay, so just at this point, do you have any questions? Okay, go ahead.
What does it mean that it's hidden? Like
Hidden, okay. Oh, okay, interesting question. Well, so you know what? So it's hidden in the sense that it's hidden in the sense that that's, you know, that you don't use it for prediction. So I don't know if it's, you know, I mean, you could, I don't know if it's really a very good name for it, but this is, let's say, you know, if someone in the 80s, probably not English speaking, or actually probably even earlier, or even 70s, you know, came up with this name, and it just stuck, you know, like a lot of things in machine learning. So it's hidden in the sense that, you know, okay, so like this is the input, right? You know what, you kind of know, let's say what it is, you know what the output is, and you know there's something in between, right? And you know, let's say like the early, you know, like the early deep learning researchers had some kind of vague inspirations from the brain, you know, like, oh, you know, this is how the brain works. So they were thinking, oh yeah, so brain is somehow processing, you know, brain is processing the data in, you know, in multiple stages. It's some kind of, you know, yeah, it forms some kind of intermediate representations, and you know, so they thought that, whoa, okay, we're just going to, you know, throw the data into this, use stochastic gradients, and everything is going to work magically. And you know, it is true to a degree actually. So you could, so I guess you could call it hidden representation or intermediate representation, but it's not hidden. It's not actually hidden in any way.
we can access it.
Sorry?
We can access
Yeah, you can access it. Yeah, you can access it. It's just like, you know, it's in the memory of your computer. It's not hidden in any way. Basically, you know, let's say, like I said, in the most simple neural network, you would just take this, you would apply, you know, like this would be, okay, so this would be basically just some kind of, you know, so basically to go from here to here, right? So to get from H1 from X, you would basically just, you know, do some matrix multiplication, you know, perhaps add a bias, and then, you know, apply some kind of nonlinear function. That's it, right? That's, so, you know, I mean, there's nothing hidden about it. Okay, more questions. Okay. Everybody knows everything about neural networks. All right. Okay. Now, like I said, look, guys. So I mean, I have been training neural networks when you had to be a hacker to train them, and you had to write code that was, you know, in CUDA. And like these days, people train. These days people just use Python. and it's it's so much easier. But anyway, so just like if you like okay, we have this main topic of this of this lecture, but like if you want to ask questions about neural networks or deep learning, you can also ask them. There's we don't have to go very fast. Okay, so yeah, okay, so like I said, so these simple models are great, but it's actually pretty difficult to solve any interesting tasks with them. So we actually need something more powerful to, well, if we are hoping to, find AI, or if we are hoping to understand something about human biology or anything like this, we're not going to do this with a decision tree, right? It's just, it's just not going to happen. Okay, so in the rest of what I'm going to talk about, I will focus mostly on computer vision because I think it's just the easiest data to explain these concepts, and actually I think a lot of the ideas in deep learning originated in computer vision, and then were somehow put into other domains, but and they can be generalized quite easily. Okay, and yeah, and again, there's a really large zoo of different methods that that you can kind of consider explainability methods in deep learning, but they mostly focus on doing something like okay, so this is the picture, make classification, and then indicate the part of the image that determines prediction, and they kind of all one way or the other fall into this category, but we'll just look at just a few because there's hundreds. But but there are, let's say, but among these hundreds, I would say probably maybe like 80% falls into maybe 4 or 5 categories. Okay, so the simplest type of method, which we call the gradient-based method. Okay, so it is incredibly simple. Okay, I'm going to explain what it does. So so I think this is from a very famous paper, but let's just focus on this column, right? So okay, so what you have is here. Okay, so on the model, here you know what the original image is, and you know what the class of the image is. Typically, so basically your X here would be an image, right? So the beta are some parameters of the model. We don't know exactly what form of the model has. And P hat again is the prediction that the model produces, right? Okay, so now, and F is some kind of a function of the predictions. So it could be, for example, either selecting the correct class or entropy of the prediction, right? Something like this. And then what we do is something really weird, right? It's really weird, but we actually do it anyway, right? So we'll so you're very used to taking a derivative of the loss with respect to the parameters of the model. That's kind of 90% of machine learning. This is not what we're doing here. We are looking at the prediction of the model. Let's just say that this F is just, let's say, selecting one element of this vector that indicates the correct class, and we are looking at the derivative of that function with respect to the input. Right? That's weird, but that's weird, but that's something, right? So basically, what you want to infer from this is you look at let's say this bird, and you want to manipulate. You're looking at whether the prediction changes a lot if you change the input. Right? I mean, that's okay. That's kind of reasonable, right? That's at least not totally unreasonable if you think about it, right? And if you do that, you get this kind of, I think. Okay, so I think here they take the absolute value of this, but this is what happens when when you do this, right? So you get, you get some sort of indication of where the object is, right? And I think it's well, it does identify it did identify this woman with with the woman with the corn and the dog, the bird maybe not so much. And that's because it's not a great method, but at least it's intuitive. And these other methods, like there's so there was a period in machine learning. There was a period in machine learning research where people were developing. I don't know, people developed probably like 100 of these methods, but they're all based on they're all based on some kind of form of this with some extra, right? So and okay, so it does it does work a little bit, but then so in this paper, salinity checks for salinity maps. People actually, like the authors of this paper were going to develop another method like this, and they decided to implement some kind of sanity checks. One of the sanity checks that they implemented was checking whether actually perturbing a trained neural network actually significantly altered the explanations. And they found that the answer was often no for many of these methods. So these methods are not super strong, right? So they are, let's say, at least not all of them, right? So they are not much better than edge detection. So edge detector is, edge detector here is, is some kind of like deterministic algorithm that just, I guess, measures contrast or something. So these methods are very intuitive, but they just don't work very well. You seem like you want to ask a question, but you're fighting with yourself.
Yes, okay. So what maybe not tell you much about experimental model, but can you help to understand how the model fits? The gradient of the top left corner, for example.
Yeah.
You see that it's maybe trying to also get some green. And
Yeah.
A guy or model swing badly right now, just give the green image, maybe find the temperature.
Yeah.
Maybe there's another utility to the gradient anyway, you just explain that.
Mm-hmm. Yeah, I mean, so you're absolutely correct that I think maybe something that's often missing in the kind of, let's say, thinking about explainability is that different people have different purposes for looking at these, and it's true that while maybe these might be useful for some tasks but not for the others, right? Or some purposes and not for the others. So it is in the it is definitely indicating that. It is definitely indicating that that this model is sensitive to the background here, right? Or or it is giving you some idea of what's happening, right? So if you let's say if you had maybe okay, so there are these kind of famous examples of of a dog being in the snow, a husky dog being in the snow, right? And the famous example is that there's a husky in the snow, and the class is husky, and some other explainability method basically found out that that this model is actually looking at the snow rather than the dog, because the husky dog is always in the snow. So it's kind of useful maybe in discovering these kinds of peculiarities of the trained models. Okay. Okay. Any questions? Okay. So would you know how to implement this? I think, it's actually in PyTorch I think it's easy. Yeah. Okay, so in your workshops here, what programming framework are you using? Oh, okay. Oh, right. Because you're not doing deep learning, really, right? Okay. Oh, okay. Oh, okay, great. Okay, so anyway, I think this is maybe a good opportunity to, to like learn something about deep learning before your deep learning block. But anyway, so what I would like you to, let's say get out of this slide is that these methods they're conceptually very simple, and they can be useful for perhaps they could be useful for some applications, but they are not in general they are not extremely strong. Okay, so now now we go to methods which are somehow more complicated, which we call perturbation-based methods. This is just one example of a perturbation-based method. This is a paper of my own that I really like. But this is but because it illustrates. Okay, so the purpose of this paper that we actually wrote was because, again, in machine learning, if you notice, there's this kind of a trend that people write lots and lots of papers, and often about very similar methods. So and then I guess in computational biology maybe it's similar, but then typically there don't exist for new tasks. They often don't exist very good benchmarks. So before these benchmarks are created, there's already like 200 methods. It is unclear how these methods relate to each other. So in this paper, me and my students were trying to simplify. Basically, we took something that encompasses maybe like 50 different papers, and we put it into one thing. We threw hyperparameter optimization at it. And we just wanted to know what we were going to discover, and we discovered that basically what we discovered was that all of these methods are much simpler than people thought. So but anyway, so the perturbation-based methods are there are these kind of methods where you want to look at the image, and you want to somehow perturb the image and see how it affects the prediction. So it's similar to the gradient methods, but there's kind of more structure to the perturbation. So there are so this perturbation could be, for example, putting a mask on the image such that we try to discover the objects such that let's say we call it mask in, right? So basically we put a mask on the object that we're interested in. And we're hoping that if we put this mask, if we find this mask, then this mask is going to indicate the most important object, right? So what we have is, so we have this masking model that is applied to this image. It produces some kind of a mask, and then we take this mask. We take this only the part of the image that is covered by the mask, and we try to do classification. So in that process, if you think about it, to do classification well, you have to be able to, not to be confused. You have to be able to say the part of the image that actually contains an important object for that class.
The first part, like the mask, was done also using machine learning or what?
Yes. So these are So we know the mask. There is the classification model here. Which maybe is a little bit. So maybe I should explain this a little bit. But basically, So this masking model is also a neural network. So these are all neural networks, right? So this mask is created by a neural network, and the classifier is a neural network. Just here the trick that we applied is that this masking network is using the hidden layers of the classifier to save some kind of, let's say, computational efficiency. But the idea is that, okay, the broad idea is that, okay, let's say, imagine it's not here, right? And then what happens is, basically, you have a neural network that generates the mask, and then this image covered by this mask should be a good image for classification, right? So it should retain all information that's necessary to correctly classify it. And of course, like these. Okay, so these like these masks can have different forms, right? So here we are just basically blanking out everything except for the object that we are interested in. But some people would blur this or do other things. Right? But it turns out it really doesn't matter. Okay, so maybe this is a simple drawing, but I would like you to understand it. So okay, do you have any questions about this? Like, do you understand why it works? Okay, does anybody want to explain how it works? No, I'm serious. Does anybody want to explain how it works? Okay. Anyway, so just to summarize, right? We want to find a mask that contains the pixels that are the most important to classification because we're going to take those pixels covered by this mask and then use it for classification, right? And of course, now you could say, you could have said, right? Why not just take all pixels, right? Why not just take the entire image? Like, why isn't this mask just everything? Well, because we have introduced some form of a regularization, right? Basically, we put a penalty on this mask such that it includes only a small fraction of it. On average, it contains only a small fraction of the pixel. Yeah.
And what exactly the first classifier is?
Oh, this first classifier is okay. So the first classifier is okay. So this is here because you need some kind of a strong representation for the masker to learn something. But so in reality, right? So I said that. Okay, so I said that. Okay, so basically, what we're going. So in fact, okay. So it's okay. So in fact, what we're going to train is, okay. Let's just say that. Okay. So there is some loss function between, between p hat of x and y. And and so this is okay. So this is the first classifier, right? Okay. And we have another loss function which is between p hat of x or with m applied, right? Or okay. So for this classifier. So for this classifier, so we need this additional classifier so that it doesn't degenerate itself. So and plus we have this regularization on m, right? But let's say in the most simple version, you can just imagine that the classifier is missing. I mean, it's a kind of, let's say, it's a technical detail for this model. Okay, but this is not the only. But this is not the only actually.
Yeah. So you said that you use this in the paper to evaluate other models. So
okay, I'm going to explain it in a second. Yeah. So basically, okay, this is not the only possibility, right? You can also there's a totally different set of methods that says you shouldn't find the pixels that are most important. You shouldn't try to classify with the pixels that are most important. You should in fact try to mask out the pixels which are most important and then erase them, right? And maximally confuse the classifier, right? So basically now, instead of selecting the pixels to train a classifier on, we're trying to erase the pixels and maximally confuse this classifier, right? that's okay. You see what I mean? Can you imagine this? No? Okay, so think about it. Okay, so think about it this way, right? So let's go back here. Okay, so we are selecting pixels from this image, and then we are trying to maximize this classifier's accuracy. Right? Okay, yeah, go ahead.
Yeah, I know that we learning, so when we create the mask,
Yeah.
we go across and but we also for the size of the mask, yeah?
Yeah.
How it impacts the problem.
How-
Will we kind of make checking that for this size of mask would be better than the other size of mask? Or we just believe that, yeah, this mask should create the specifications, the size of the windows, which we move to the images of
What we do is we put a penalty. Okay, so let's say this is the loss function that we have to. Okay, for this case particular, this is the loss function that we're optimizing. So we are well. Okay, this actually I think there's. I think there's a mind definition, maybe additional values here. But anyway, so what we're trying to maximize the accuracy of the classifier that's acting on the unperturbed image. We're trying to maximize the accuracy of the classifiers acting on the perturbed image. And then we are also adding some regularization to the size of the mask. So basically we're trying to find the smallest mask. Right, so there's some lambda here, right? So we're trying to find there's a hyperparameter. We're trying to find the smallest mask that gives you the highest accuracy. Does that make sense? Okay. Yeah. Okay. You had a question. No. Oh, it was just okay. Okay. All right. I hope everybody understands that, right? So now this is just a little bit more convoluted, right? But not that much. So here, what we're doing is we are again trying to find a mask, but we're trying to use this mask to erase the important object, and we are trying to maximize how confused the classifier is. Right? So the measure of confusion is the entropy of the prediction. So if you have a very high entropy, you don't make correct predictions. Right? Yeah.
So would the classifier be the most confused if we erase all the pixels?
Yes, but again, if you did, okay, but again, there's a penalty for there's a penalty for the number of erased pixels. So you're trying to find the mask that maximally confuses the classifier with the smallest number of available pixels. And there's of course some penalty on these pixels being contiguous, right? So because you could confuse the classifier by erasing pixels in random locations. So there has to be some kind of penalty for actually, for these pixels to be next to each other. Okay, does it make it a little bit more straightforward, or not yet? Okay.
Do you apply then the both in and out to get like the final? These are the most important pixels.
So so basically what you can do is you can kind of mix the two, right? So you can exactly try to you can have both of these objectives at the same time. Okay, but anyway, but I would really like to try to make sure that you understand this. Okay, go ahead.
Does it mean if the network deep learning isn't not confused by the background, that it relies on like information in the background that is not actually the feature you're looking for? So if it's very confused, it's not looking for anything in the background but the actual feature you're looking for. Exactly.
Okay.
For example, of the snow and husky you had. Or?
Yeah. Okay. That's a good example, right? So the thing is that there are different ways of, so there's an additional layer of complication that I'm not talking about here. But because conceptually this doesn't help you. But you're right that if you you're correct that sometimes if we just literally apply what I said, then the background maybe would be more useful than the object, right? But let's say on average, this wouldn't be true, right? So it's and also there's a penalty on the size of this mask. So the object is typically smaller than the background. So you can control for this kind of effect by different types of regularization. But the important part is that you just have to you just have to find the part of the image which contains the thing that you care about. If you erase it, then the model doesn't know what's in the image. So I think maybe the confusing thing is that the objective here, maximizing the confusion of the model, is different from the objective here, right? Because here we wanted to maximize accuracy. But you can put them all in the same model. And basically I would the way that would work is I would have to add more terms here to this objective that I'm optimizing and just add more hyperparameters. And if I have enough computational power, I can throw in, maybe I can train it for, maybe I could optimize these hyperparameters by training very many random sets of hyperparameters. And then through this process of hyperparameterization, I can find which elements of this called framework are actually important and actually increase accuracy or actually increase performance. Okay. Right. Okay. So maybe let's go back here for a second. Okay, guys. What do you think of? Whoa. Okay. Do you understand everything here so far, or do you have any more questions? Okay. So let's keep going. Okay. So there's another set of methods that actually embed explanation into the model. And I think this is actually a very interesting set of methods. I actually like to work on them myself. And they all, let's say, there's a variety of them, but the most popular one that's actually is used in practice is called this class activation mapping. And it is doing something, again, fairly simple, but very effective. So here you see these conf, right? So this is something called convolutional layer. You can just think about it as, so these are different hidden layers, but these hidden layers have a special structure. So I think so in a way you can think about it as, these hidden layers as, not being just one vector, but being a tensor, right? So and each slice of this tensor represents detection of a certain feature. So you must have seen these kind of images where where you have where you have heard of Gabor filters, right? So in a way you can think about it as maybe in the very bottom of this network, each slice of this tensor would, for example, detect certain type of edges, right? So maybe so they would be having, let's say, so you could have maybe 32 types of edges, and you can compose these edges into something more complex. And eventually what you will have is like in this layer here, you would have some kind of a each of these, okay, so let's say these are multiple slices in this direction, and then for each of them you have this kind of a matrix. So the way it would work is basically each of these slices will detect something, right? So maybe one of these slices would detect ears of a dog, right? Another slice maybe would detect face, right? Or another one would detect, let's say, something like a window, right, on a very high level. Of course, this is not as clean as as I'm telling you, but this is a kind of like a high level idea. So, but if this story is true, that if this story is true that these features had this kind of interpretation, then you could just take global average pooling on each of them, right? Like here, and you would have one number for basically would be one number representing, let's say, how frequently detected certain features are, right? So maybe this first feature could be, okay, how much this model is thinking that there is a face here, right? Maybe how much this model is thinking there is a dog here. How much this model is thinking that there is a window, right? Or maybe a cat, right? So if you accept this interpretation, then then you also have to, so then then you can use these, basically then you can use these kind of concepts, or let's say kind of these concepts to actually, to make a prediction about the final class, right? So this is just the logistic regression layer with you can think about this bit, right, as just a logistic regression where you have some features that are more well defined. Yeah.
So in the end, would you be able to try to remove certain features as such that you retain the minimal amount of information that allows you to identify whatever tree that you're trying to do?
Oh, okay. So what? So so there are So I think one thing is that first of all, these features are kind of automatically discovered. So you don't really know what they are.
It doesn't matter. You just it doesn't matter the amount or
Sorry?
since they are automatically generated, it doesn't matter the amount of information that you're looking for.
So I don't think I understand your question.
Sorry. So my question is like you look at each one, but you mentioned that one will be able to identify the years or the all of it. So would you just eliminate some and still be able to get the final indication?
Oh yeah. So So yeah. You possibly could, right? So you could. Okay, but how would you do this, right? That's the cool part, right? So maybe you could. Okay. So of course that you could, for example, add some kind of sparsity penalty to this, right? So for example, you could maybe ask this network to make these kind of predictions, but you would maybe make it really, really difficult for this network to use more than 5 concepts, right? Like you can do this. So, but let's say, but for the purposes of finding an explanation, the way people use this is like super simple, right? So basically, what they do is they compute these numbers, and then they actually look at, these kind of these feature maps before collapsing them into one number, right? So they would have. Okay, so maybe this is what the blue feature map looks like. You multiply this by the number associated with the feature map, and then you sum this up together, and then you say, okay, like this neural network is looking somewhere here, right? This is a Australian Terrier, right? So you can so it's this Australian Terrier is somewhere, right? So this model, let's say it's an automatic way of okay, so this is I think it's a very good method because it's super simple, right? It's no problem. That's a little bit not appropriate. Okay, and then there are so here, as you notice, right? This model is not trained with any kind of information on the location of the subject. Right. So this is totally automatically discovered. But so that's why I call it weak localization-based methods. But then there are let's say strong localization-based methods which are trained not just with the class of this entire image, but also with the location of some specific objects. Right. So here, here the class would be, it would be like a single class, of this object, there will be, you know, they will say that, okay, here there's a seagull and here there's a seagull. Right? So you could, okay, so you could use this, so you could use this kind of methods to do classification. If you say, for example, take the, you could, okay, so you could for example take the prediction from this model that's most confident and make it your classification prediction. But they are trained with just a richer set of labels. Okay, and the reason why I'm showing you this is not that because I want to explain how this model exactly works to you, because it's very difficult. And that's exactly the point I'm trying to illustrate. That, you know, these kind of strong localization methods, they are working very well. They are actually very effective. You know, like this is the way. Let's say if you wanted to, if you actually, I think like if you had the data with this localization of these objects, that's what you should always go for, because there's so much knowledge about location of the objects in comparison to having just the class for an object. But these models are ridiculously complicated. Oh, why are you decoding and decoding? Oh, okay. That's a good philosophical question. You know, so I think, okay, so you know what? I think these names are a little bit. So I think like hidden layers. You know, I think there are some historical reasons why these things are called encoder and decoder. I think in fact here I don't know if you could really say that you're encoding and decoding. I think in a sense, you know, like in a sense you could think about it as, you know, let's just say you could think about this as encoding certain knowledge with this very complex neural network, and then trying to decode it with another neural network. Because, and you know, and introducing this kind of, and often in machine learning, it's been shown that, you know, putting this kind of structure of an encoder and decoder puts a constraint on the knowledge that you can, on the information you persist in this decoder network. So historically, when there's, you know, historically people call this encoder, but you know, but they are not really like it's not a decoder in the sense of, you know, like I don't know, like signal processing or something.
Weren't they developed for natural language processing? So they were firstly like transformers developed for like processing text. So that's why probably they call them encoders.
Yeah, but you know, yeah, that's true. So, but there are, you know, but this encoder decoder, let's say vocabulary that, you know, that exists for, you know, like 30 years. Like it's not a part. So again, the transformer networks, which are part of this model, like borrow the vocabulary and somehow make it actually more appropriate in their context. But anyway, so what okay. So the reason why I'm showing to you is that, you know, like these models are really effective, but they are really difficult to implement. Like in fact, they reach this kind of level of sophistication in, you know, that it will be, you know, it will be very difficult to re-implement. So you know, as opposed to, let's say, logistic regression, like everybody implements logistic regression all the time. But for something like this, you would actually, you know, like you wouldn't actually do this yourself. You would just download the code from the authors if they provide it, and maybe try to adjust it to your needs. But you would never actually like try to like re-implement it from scratch, because that would take you, you know, months or maybe even impossible. Okay. So guys, do you have any questions here? Yeah, go ahead. Oh, so okay, so these methods, okay, so we know, so these kind of methods actually, I would say maybe overfit a little bit less actually, because they have such rich supervision, right? Because the, you know, like pointing to the objects is a very rich form of supervision, so it's much harder to overfit to that. Okay, cool. Okay, so you know, okay, now we have 15 minutes. So I was just going to show you some kind of a project that I was working on, but I'm just going to, you know, there's just not very much time, but I'm just going to like show this to you. I will just skip through some things that are maybe less interesting to you. But okay, so so basically I'm just going to show you something that, you know, like, okay, so this is a pretty interesting and difficult project that I've been working on for 6 years with a few students in computer vision. So what it is about is that, okay, basically what we want to do is we have these 4 images, not just one, and we are trying to, we're trying to decide whether this person has cancer, and we also ideally would like to point to the cancer. And so this is kind of like a part of, it's very complicated of how actually, radiologists and pathologists actually reach the conclusion that someone has cancer. I guess you probably know this much better than me, but here we are just skipping all of this, and we are just only trying to predict all of this based on these images. And we treat it as a machine learning task, right? So we have we have these images, we have some kind of a learning model, and then we're trying to decide whether this person has cancer in the left breast, or maybe something that might look like cancer but it's not cancer. These are called benign findings typically. And then whether someone has the cancer in the right breast, or something benign in the right breast. And okay, so the difficulty of training anything in machine learning, any machine learning on medical images, is that public data is actually often not available. So you really have to keep in mind. I guess in biology you have similar problems. So like ImageNet, right? This kind of very famous data set is 40 million images, and so the DSM is a public data set of breast cancer images, and it has 10,000 images. So, like we wouldn't be able to do anything interesting with this. So we worked ourselves. We extracted data from our hospital, and we found about 1 million. Now we have probably more like 5, but this is on one slide. But it's really just difficult. It's really just difficult to do this work because data is not available. And now, okay, so maybe this is something very educational. Can you see the dot? Can you see the dot in the left bottom corner? Can you see it? Okay, so it's not a dot actually, right? It's a picture. Believe it or not. And I bet I bet some of you already know what this picture is. Okay, so what is this?
A panda.
So what, sorry?
A panda.
Panda, okay, interesting guess. Okay, any other guesses? Huh? Okay, any other guesses? Okay, nothing?
Some speed scan?
Sorry?
One slide from speed scan or something?
What kind of scan?
Computer tomography.
Oh, okay, no. So you were correct. This is a panda. yeah. You know what? I think this is something that we don't appreciate in our everyday lives. But the fact that we are capable of making predictions about classes for such tiny images is just evidence that a lot of compression is possible, and you still are able to retain the information that's necessary to make the prediction. And that is true for natural images. And I think this is a very important property that's actually used by many of these networks. But this is not true for almost any of medical imaging, or whether it is pathology or radiology or whatever. You wouldn't be able to guess. In fact, even radiologists wouldn't guess from that picture, because they would say this is like too tiny. There's like not too much light or not enough light. Not enough quality of the screen, etc. So you really have to work with these really massive images, and there is no way around it. So that's why. So we have this kind. So we developed this kind of a model that embeds some of these principles, and I will explain how this works, and that will be probably the last thing that we're going to do today. So we have two. So we have two assumptions here. So one is that we can't process this image with a very high capacity network at once, because the memory of the GPU, which is used to train these models, is limited. So you cannot, and these images are huge, right? They're like 2,000 pixels by 3,000 pixels. So, like these days, like the modern GPUs can maybe, the modern GPUs are designed such that maybe they have, maybe, I don't know, like 80 gigabytes of RAM. And, and then neural network, the problem is that, if you process this X through many, many layers, right? So like the common networks have maybe like 100 layers. You have to store these in the memory of the neural network. And if the network gets deep, it suddenly becomes difficult. So you cannot really have a very high capacity network applied to these very high resolution images. So what we did is we created some relatively small network, and we applied it to these images, and we used something very similar to this model that I've shown you a few slides ago, which was detecting this dog, right? So this relatively simple model identifies a part of the image where it is likely that something important is there, and then it is sampling patches in these locations, and it is then applying a much higher capacity network to a subset of this picture, synthesizing the information from these different patches into just one vector, and then synthesizing information from this low capacity network and the high capacity network. So from the global, what I call the global module and the local module. And this way, we can train. So this way we can train something that's, basically a very high capacity network on a very large resolution of an image. And it has this very convenient property that it is not just indicating what is the predicted class of this object. Here, whether this is cancer or not cancer, but it also localizes this cancer if there is a. Okay, and actually, okay, maybe let's keep that. Let's do this. The very interesting thing about this model is that because we train it only with the class level labels, we're actually identifying some cases that radiologists thought the cancer is invisible, right? So we often have, in medical diagnosis, it often happens that there are different stages of the diagnosis, and some imaging modalities used at the beginning are less powerful than the ones at the end, because they are more expensive and slower. And so here, for example, so here this was an example of of an image where the radiologist thought, okay, maybe there is no cancer here, but but those tissues form these kind of like complicated patterns, so you can't really see very much. So someone should look at this under the ultrasound. And the ultrasound, yeah, they did find something that might look like cancer. But our model was actually capable of indicating this based on this X-ray image. Like, we didn't need the ultrasound to figure this out. So it is okay. So I think this is like a small thing, but it really, I think it's actually an indication of something very interesting. That if you have really a lot of data and high quality labels, you can actually discover some kind of knowledge or some kind of things that just humans are somehow either imperceptible to humans or very difficult to perceive for humans. Okay, so of course we have. Okay, I'm not going to talk about this because that's I guess not a great time. But we can generalize this to. We can of course generalize similar ideas to other types of imaging modalities. Also even to like COVID. Okay, but I think the interesting, like I said, I think the interesting thing is about all of these interpretability methods, especially I think if we have good methods that would also somehow embed causality in these methods, is that we might be able to discover some kind of new knowledge, right? And what I mean by that is, I think you computational biologists are very big for this. That's so let's say when I attended classes at university about things like biology and stuff, then they were always kind of like this kind of a blueprint of how a computational biologist should work, is that Okay, if you have some problem, you should talk to an expert, read a lot of books, and think of some kind of very appropriate model for this kind of a process, right? And this, I mean, would you agree? I think every reasonable person would agree that this is, this is kind of, so this is a kind of, let's say, standard way of acting in these biological sciences or physical sciences. So you take some knowledge and you somehow try to embed this knowledge in a structure of some computational model in which then you do learning and inference. And this is great, but if you have millions and millions and millions of training data, then you might actually do the opposite, right? So you might be actually able to train some kind of very generic neural network and discover some kind of structure in your data using this neural network. And then, then you discover new biology and you win Nobel Prize. So I think this is really the way to go. So, okay, so in conclusion, I think explainability is especially important in things like, like you work on, like life sciences and medicine. I think, this model that I presented is going to be somehow, like this, not necessarily this model, but a lot of models like that will be very popular. And it's definitely going to be superhuman. I already have experiments that show that these models are superhuman. And it's going to only get higher. And you can use these, you can use this kind of models to discover knowledge, and this is going to be a hot topic, I'm sure. Okay, thank you, and you can, ask questions. Yeah.
So in the model for breast cancer, you said that it has like 4 parts.
Yeah.
So what is the purpose of the final part when it like combines the original big animations with the decisions from the smaller parts?
Yeah.
Because basically, classify the smaller parts, otherwise there needs to make them.
Okay, well, because maybe so to be honest, I think it doesn't make a huge difference because you're correct that you should very often just be able to make a correct prediction based on based on just the raw objects, right? But sometimes the context of the global context is useful, right? So it's for example, you might be so let's say that if you detect something very tiny, right? Let's say that you have a picture of let's say you have a picture of some kind of a snowy terrain, and you detect something tiny in it, and your network thinks it's a canary. Canaries don't usually live in the snow, so this indicates that maybe your local model somehow makes decisions which is incorrect. So this global context somehow lets you gives you an ability to maybe make a second guess if you think it's completely wrong.
I have a question, because we are doing using the explainability models to explain our context models. So we need to tell if we trust our classifier. And how can we say if we could trust the explainability and the explanation? Because if we have, for example, this classification of images, we are looking for birds, and it's easy to see that if we have this explanation, so we have this bounding box around the bird, so we can see that, oh, okay, it's a bird, so everything is fine. But sometimes maybe we are not able to tell if the explanation is correct, because it's not
Human evaluation study.
So is there any methods like measuring or something like that to tell how accurate is the explanation? If we have, for example, also numeric features, not convolutional networks, but NLP, we can see like this visualization. Which is nice.
So if you can define what the correct explanation is, then you can always just compute some kind of a difference between your explanation and the correct explanation. If you can't define it, and often you won't be, able to do that, then you have no choice but to, let's say use an expert, and you can, an expert can either make a binary decision, oh, is this a good explanation, or maybe compare between different explanations. But you're absolutely correct that this whole there's a problem in evaluating these kind of methods. So like typically it's either some kind of numerical evaluation, assuming we have a ground truth for a small subset of the test data, or human evaluation.
So we don't,
Sorry?
we don't have any methods metric to evaluate tests.
Well, okay, there's no metric or method to evaluate explanation in full generality, because a priori you don't know what this, okay, so this metric, or it has to be somehow related to how you're going to use it. So I'm not going to, there's no silver bullet for this. You have to make it specific to your application.
As for example, if you want to predict, I don't know, COVID-19 at the X-rays, mass, and we use, for example, the guided breadcrumb. And I've heard that those maps created by guided breadcrumb are not always accurate, so they may be blurred or something. And sometimes we have cases where we are not able to tell if there are actually some changes or we don't see them. But if you want to use those classifiers in hospitals, the medical
So
to be able to trust the model if they will use it in hospitals. So we actually have to provide the explanations.
Okay, so you have to you have to either make some kind of create some kind of a test set where you're confident about let's say when you can actually annotate and you're confident about the explanation that maybe given by an expert, or you can have some kind of summary statistic and you can check whether the summary statistic somehow is somehow correlated with your explanation. But in general there's not going to be a universal method for validating it.
I have a question regarding, I wonder where you see in the clinic, like, test usable. I think I'm wondering if you want to model to be used like, before the doctor sees the result, for example, look, I think this is suspicious, look at this closer, or after the medical assessment, the model will be like, and the doctor, for example, thinks that it's like a intermediate phase, they can into the model, like for circulation, so I wonder where.
Okay, I think that's a very good question. So, I think this is. So I think it's a problem for psychologists more than computer scientists. So we have, we had exactly this problem when we were implementing this at NYU. And we were debating this for months. We're debating this with.
Because this is the issue with those classifiers for the distance, like for this work. But I think like this thing to propose is a big advantage. Like explainability, which is great, because it's much easier for the doctor to be able to tell like why this.
So so in practice, what we did is it's actually something I think. I think in medical settings, people typically tend to be very cautious because there's a lot is on the line. So what we have actually concluded is that in the first phase of how we're going to deploy this, we are just going to filter out the cases where the model is very confident that the person is healthy. right? So basically, so they don't do these kind of additional follow-up procedures for very healthy patients. And right now, we are not even showing any explanations. So we're not showing explanations for the patients that the model thinks this person could have cancer, because we don't want to bias them to thinking that, oh yeah, this is cancer, right? But,
One thing I wonder if it's not correctly, but differentiate two left and right.
what do you mean?
Because you showed earlier that you start left breast, cancer, cancer, right breast, cancer, cancer. So it's just a way of showing this, or not right, like somehow, like it is.
So of course, so this is okay. So it's the same network for left and right.
Okay.
It's just it's just it's just like, but conceptually that's what it is. Okay, questions or everybody? Oh, cool. Question.
Yeah, thank you. I'm not the expert on this. I want to ask you something about maybe something that I struggled in terms of the neural networks and how I can do it in my daily practice. I'm trying to find biomarkers for a very complex disease.
Yeah.
And so I thought in a way that I have, let's say, many features from a biopath. And I thought that I could use a neural network as a way to see how much accuracy I can get.
Yeah.
And then, because I have this almost the maximum accuracy that I can get, then I can build a more explainable model that actually tries to mimic that accuracy.
Yeah.
Is something that you guys think of, like building, neural network that explains less to something that is more explicit?
Okay. Yeah, I see your point.
Shifting the things between more explainable and less explainable?
Yeah, so I think this is actually something that I think there is a bit of a so where was my slide? So it's I would say that there is a little bit of a myth that there exists some kind of explainability, expressivity trade-off. And it is okay. So I think if you think about, let's say, neural networks within a certain class, then let's just say logistic regression is a form of a neural network, right? Very simple one. So then it is true that if you move to, let's say, networks with more layers, they suddenly, like more than 0 hidden layers. Then if you have a hidden layer, then suddenly it becomes less explainable. But often putting explainability in the model actually makes the network more accurate. So if you can somehow, let's say, for example, if you can think of additional targets that somehow lets you explain the prediction and just predict these intermediate targets and then find the prediction based on these intermediate targets, that's making your network in a way more complex, but also more explainable. So it is. I think it's so. Of course, so you shouldn't necessarily think of this as being like a very hard rule that you cannot have an explainable and accurate network. That's just not true.
Yeah, I was just starting to say that to actually find the biomarker itself. That's the objective.
Yeah,
So because the neural network will give you the accuracy, then it doesn't really identify the biomarkers themselves. They actually.
Okay, so you can, if you want to find some biomarkers, then I think what you should do is you should perhaps, I don't know what form of data you have, right? But I guess probably I can tell you how I would do it if I had to if I had like 30 seconds to think about it, right? So basically what I would do is I would implement something like this. And then I would, then maybe I would look at maybe 100 examples of what your network found, by an expert, and see if it makes sense. And then you maybe would discover some biomarkers. Maybe they are somehow meaningful. Like that's the kind of obvious way how you can use explainability for your purposes. One more question. Okay.
I have a question more
Okay, sure.
philosophical maybe, but from what I have seen, the neural networks that are targeted towards image processing basically any kind of either categorization or even generating images from sentences.
Yeah.
Tend to be like the development tends to be much more forward than other types of networks that works on features, basically. Like there seems to be some kind of upper cap on accuracy that neural networks can achieve, like from just physical features rather than from images.
Okay. Yeah. So so it's not that. Okay. So it is not that neural networks don't work for feature, like where you say features, right? Tabular data. Right?
Yeah.
Neural networks work for tabular data very well, but the strength of neural network in something like image recognition is that if I ask you to define the visual features, you would be completely lost. You cannot somehow go and write down you cannot write down like how to detect a cat.
Yeah.
Right. So the network can automatically discover these features, while in tabular data typically already has a very strong structure. So basically there is just not as much as you cannot gain as much through the network through deep neural networks because like someone has already done this work for you. But if there exists some kind of complex combinations of features that that somehow strongly correlate with the target, then neural network will find that. Okay, guys, I think this is okay. I think I'm like 15 minutes late, so I mean, you can ask me. You can ask me, questions like I don't know during lunch or something, because I guess probably there's like a next talk or something. So.
Right now we have coffee break.
Oh.
The next talk should be 15 minutes, but I think we will extend the coffee break.
Okay, thank you.